All right, let's go ahead and do this. Today we are going to talk about the chemistry of planet Earth. Last week with chapter 11, we kind of touched on the society part of society and chemistry, talked about nuclear power and blah, blah, blah. Today we're going to extend that. We're going to start off talking about the Earth itself, its construct, the cores going up, the mantle, the crust, and the atmosphere. We'll talk about things like global warming, ozone depletion, pollution, whatever. Before we get started though, on Wednesday, we're going to do our second part of society, chapter 16. Now, chapter 16 is really fun. It's about food and human nutrition. Following this lecture, quiz number 2 will come online, and sample E2 will also come online. Basically, we have until the following morning or following Monday to finish quiz number 2. Now, because we had a 2-week spring break, the syllabus has changed a bit. Last Wednesday, we did chapter 11. No more labs, sadly. Today, we're doing chapter 12. On Wednesday, we will do chapter 16. And as soon as we finish that, quiz number 2 will come online. Quiz number 2 will basically concern itself with the first 9 chapters. Okay, not the later stuff, just the first 9. The following Monday, so we're at the 4th of May now, we will do exam 2 review. So when quiz 2 comes online, the sample exam will also come online as a hard copy that you can print.
Mr. Young, would quiz number 2 be multiple choice?
Yeah, well, it's a mixture of multiple choice, short answer, calculated numeric, whatever. Exam 2 review is also going to be present online as a Blackboard test. So look at the hard copy, figure out the answers, go to the exam 2 review, and answer them. This will get you 10 points or up to 10 points if you do this. On Monday, May the 4th, we will do the presentation of exam 2 review. And the following Wednesday, so this is May 4th, 5th, 6th, we will have exam number 2. Exam 2 will include questions from chapters 11, 12, and 16. You know, maybe one question for each chapter, but something like that. I'm almost afraid to say it, but any questions?
Yes, sorry. How many attempts will we have at the review?
You know, I'm not sure. I just might make it unlimited because it will be the same basic format as the exam. And I want to make sure that if you don't do well on the exam, it has to do with the fact that you know nothing, as opposed to the format doesn't work for you. So I want you to get as much exposure to the format as you possibly can. Frankly, I'm sure everybody's going to do great. All right, let's get started. This is the Earth. It's a very classic picture. When people started going to the moon, we could take pictures like this. It's an actually amazing sort of shot. The Earth, starting from the inside out, looks something like this. The inner core. Remember, the Earth has a lot of gravitational force pushing everything in. In the middle, that's the highest gravitational force, and it's enough that it can take and make this inner core extremely hot, but it's still a solid. It's about 800 miles across, big solid ball of iron nickel alloy. Now, as you work your way out, you get to the outer core. The outer core is basically the melted version of the inner core. It's a very viscous solution. Again, it's very, very hot. Working our way up, we hit what's called the mantle next. Now, instead of this being iron nickel alloy, this is actually a silicate rock conglomerate. So there's basically the same stuff we see up in the crust, plus a whole lot of heavy metals that we don't. But this is a fluid, and it's very hot. It goes from about 4,000 degrees here up to maybe 500 as you approach the crust, but it's still very hot. Think of this as molten glass. Okay, imagine melting glass. We expect that to flow, but very slowly, highly viscous, somewhat amorphous. On the top, we have the crust. There are two types of crust. We'll call it continental and oceanic. The oceanic is under the ocean. This weighs a lot. It squishes it down and makes it very dense. Continental crust is thicker. It's older, if you will, even though it does recycle into oceanic very slowly. Plate tectonics. Remember I said that the mantle is like a molded glass, and because of that, it's a liquid, but it's a very slow-flowing, very viscous liquid. This is an illustration of what that might look like. We have the outer core here that's very hot, and it's enough to cause upwellings in the mantle area where we have hot spots forming. They rise up, it gets cooler up here, and it kind of disperses at the top. This is a convection current. It happens constantly all over the Earth. Plate tectonics basically refers to the fact that this upwelling of mantle from the outer core up to the crust causes a pressure in the crust that basically causes anywhere that you have a weak spot that this will break. As it breaks, it is replaced by stuff from the mantle. The original crust is kind of pushed to one side and the other, and it goes down back inside the mantle, where it's eventually recycled. Now, this is a very, very slow process, but it's a continual process. This is what we call plate tectonics. Now, the word plate refers to the fact that the land masses in the crust are broken up into separate plates. These are chunks, and they have boundaries. The boundaries are defined by the upwelling and the returning to the mantle of the crustal material. This has many effects, and we're going to talk about some of those. This is a map of the plates. Up here, the big brown thing, this is the North American plate. Covers North America, Greenland, this is part of Siberia. This is the Pacific plate, basically the ocean. Australia is here. This is the South American, the African, and the Eurasian plates. At these little black lines is where the crust has broken apart due to the upwelling of the hot mantle. Now, we refer to this point where the crust breaks as a divergent boundary. And once again, what happens is mantle comes up, the crust breaks, goes and it dives under other adjacent chunks of crust, again at weak spots. As it drops down, it gets really hot again. That tends to set off volcanoes, builds mountains, and stuff like that. The process of one piece of crust diving under another is called subduction, not seduction, subduction. Don't forget the B. Two continental plates or the oceanic plates collide. The more dense oceanic will tend to typically dive underneath the less dense continental. And as it does, this stuff begins to heat up. At the junction of these two, we have volcanoes form, lots and lots of earthquake activity, whatever, because we're basically breaking the crust as this happens. Examples. A few years ago, Mount St. Helens up in Washington State blew its top quite literally. And again, it's an example of this mountain range, the Cascades. And this is formed because we have the Pacific Ocean crust here diverting under the North American plate, causes great friction, lots and lots of heat forms. We divert some of this material to make mountains, and of course, volcanoes erupt. A really classic example of all of this is the entire west coast of South America. This is the Andes mountain range. One tremendous mountain range all along this entire continent. Lots of volcanoes, lots and lots of earthquake activity. This again is caused because the Pacific plate is going underneath the South American plate. As it does, it builds mountains and sets off volcanoes. Earthquakes, of course, because we're just breaking the crust, and as we do, things shake. Any questions? Well, this can happen in the middle of the ocean as well. If one chunk of oceanic crust just happens to dive underneath another, we get exactly the same phenomena. As the stuff dives down, this originally was a weak spot, we wind up with a trench. The Marianas Trench is an example of this in the Pacific Ocean. It's like 20,000 feet deep. It's just amazing. But as it goes down and heats up, we get volcanic activity occurring on the surface. As the volcanic activity persists, we get islands. This is where Japan came from. Pacific plate, Philippine plate, Eurasian plate, they all meet right here. We have massive, all of these little red dots are volcanoes. We have mountains, we have volcanoes, and we have Japan. Once again, you can very clearly, by just looking at the volcanic activity here, dissect one plate, two plates, three plates, and again, Japan. In chapter 11, we saw the power plant that was destroyed Um, following an earthquake, it was just about right up in here. Not surprisingly, I mean, huge volcanic and earthquake activity all along this juncture. Bad place to build a power plant. If you've ever noticed, Alaska has a chain of islands called the Aleutians that form a really nice smile. That's because they are at the junction of the Pacific and the North American plate. This is the trench, the Aleutian Trench, and it marks the border at which one dives under the other. Again, we get all these volcanoes and all these little islands. Kind of a neat thing. Well, just like we could have oceanic crust go under one another, we can do the same thing with continental. When we do, we don't get islands, of course, but what we do is we get huge mountain ranges as this thing literally pushes the crust up to form these mountains. It dives down, the usual sort of thing. We can get volcanoes in here, typically not though. Typically these are fairly stable. Um, we can get spectacular mountains. Think Switzerland, think the Alps, think Mount Everest. These things are formed from continental crusts caving in underneath each other and pushing everything else up. In chapter 11, we talked about a less impressive, perhaps, mountain range, the Yucca Mountain. This again is where the US government decided they were going to bury their radioactive waste. Now, hopefully by now you have figured out that the last place in the world you would want to bury your radioactive waste is under a mountain. Because where did that come from? It came because plates were colliding, they were breaking, they were pushing stuff up. This is the Yucca Mountain Range. It's broken. Earthquake fault running right in the middle, right next door to the prime storage area for all of this nuclear waste. And again, 500 yards literally from the water table. Not a great idea. Any questions? Well, this entire process of the mantle welling up, hitting these weak spots, pushing things around, leads to the phenomena of continental drift. Now, I'm sure when you first saw a map, like when you were 2 years old, and you saw South America and Africa, you kind of said to yourself, oh my goodness, even if you couldn't speak well, oh my goodness, those kind of like fit together, don't they? Well, yeah, they do, because they used to be attached. This is the border between one plate and another. In fact, everything used to be attached. Going way, way back, all of the continental land masses were contained in one giant continent called Pangaea. As the process of the upwelling and the cracking in the crust occurred, these all broke apart to make the continents as we know them. Let's take a look at a really cute animation of this process. Here we're starting with the old continent. We have cracks all throughout the crust. The upwelling happens, and slowly they start to move apart. We're starting to form Asia up here. North America breaks apart. Antarctica, Australia, and this is India. These two finally break apart. South America moves up close to North America. And I was talking, so you might not have noticed. But did you see what happened with India? India started down here, wound up here. Let's look at this one more time. We're assembling Eurasia. Antarctica goes down. This is India. One of the last great movements. It just goes and heads up and smacks Asia right in the belly. This is why we have such magnificent mountains here in Tibet, because it just really rammed into it. Any questions? All right. The crust typically doesn't work its way, or the mantle typically doesn't work its way up to the crust, and that's a good thing. Up here, we like silicates. We like light atoms. The crust has lots and lots of heavy metals in it. For the life forms that have evolved where we happen to live, those heavy metals like lead can be fairly toxic. There are a few places where this has happened, though. This is actually mantle that upwelled. They're very rich in heavy metals, good place to mine if you want to make lead, but if you notice, nothing lives. Very, very toxic with all the heavy metals. The crust is really rich in silicon, magnesium, iron, and oxygen. This is an ordering. As you see, oxygen is really up here, magnesium, silicon, iron, and we get other stuff. The compounds that make up most of it, silicon dioxide, 46%, magnesium oxide, iron oxide, aluminum oxide, whatever, simple oxides all the way down. Silicon is the greatest. Now, where we do have bits of mantle that show up, we can mine it. We refer to these things as ores. Sometimes we have to dig down to find them. But this is an example of iron ore. This is manganese ore. Remember, we can take iron ore, which is iron 3 oxide, react it with carbon monoxide. This is a single replacement reaction, and we get iron. This is how we make iron in Gary, Indiana. But the real winner in the crust are silicates. A silicate, it's a tetrahedral polyatomic ion, so 109.5 bond angles, charge of -4. It is extremely common in the Earth's crust. Exists in a huge number of forms. This is a zirconium silicate, kind of a crude sort of thing. This isn't what you're thinking, cubic zirconia, that's zirconium oxide, but the silicates can still be remarkable gem quality compounds. For example, the manganese aluminum silicate looks something like this. Beautiful, beautiful crystals. Here's one with uranium in it. Now it's radioactive. Probably shouldn't wear it on your finger, but it is a very nice crystal. Again, this is a copper chromium version of the same sort of thing. But the real winner is silicon dioxide. We refer to pure silicon dioxide as quartz. Quartz is a tetrahedral crystal. This is what crystallized quartz looks like. It's beautiful stuff, really is. And this is a model of the conjoined silicon dioxide molecules. You see, they form a remarkable three-dimensional array. Quartz is sand, quartz is glass, quartz is in everything. However, silicon dioxide can crystallize in different ways. Instead of using it as a three-dimensional form like this, where we make countertops and stuff like that, you can instead crystallize it in a two-dimensional array. When we do that, we get basically a flat structure. This is the mineral we refer to as mica. If you have a chunk of mica, you can actually peel these layers off very carefully. They're transparent. You can see through them. In fact, back in the old days, the very first heat-proof see-through ovens looked something like this. And this window that you could see through, sort of, was a sheet of mica that had very carefully been peeled off. Again, it's silicon dioxide, so it was heat-proof. Any questions? Now, the real killer, quite literally, for silicon dioxide is silicon dioxide that crystallizes in a one-dimensional array. So instead of two or three dimensions, this is just a single strip of silicon dioxide. This is what we call asbestos. If you dig asbestos out of the ground, it kind of looks like this. These are little tiny fibers, and they represent a one-dimensional array, again, of silicon dioxide. Silicon dioxide is basically sand. Nothing happens to it. It's impervious. And if you crystallize it in a single strip like this, it's a very sharp little fiber. If you happen to inhale this, it goes into your lungs and it can puncture the mesothelial cells on the lining of the lungs. This is a pleural mesothelioma. That's why we don't use asbestos anymore, but my gosh, it used to be everywhere because it's a perfect insulator. It's just a great sort of stuff. Only problem is you can't breathe it. If you do, you get cancer and you die, and it's not nice. Any questions?
No.
Finally, you can take silicon dioxide. It's not a three-dimensional structure or a two or a one. It's an amorphous structure. This is what we refer to as glass. This is silicon dioxide, totally amorphous. You can melt this, you can pour it, you can make martini glasses, you can make anything in the world you want. Again, it's very viscous material, high melting, but again, you can shape it as you like it. The viscosity of this is very similar, like I said earlier, to the mantle itself. Very hot, moves very slowly. Actually, glass is technically classified as a liquid. If you let this martini glass sit for a very long time, it will slowly flow down into a puddle. Now, silicon dioxide has one other very important side effect that really isn't understood chemically on a great scale. But instead of talking about silicon compounds, let's talk for a second about calcium carbonate. This is limestone. It was known from a very long time ago. So we're talking 10,000 years. that you could take calcium carbonate, heat the heck out of it, so a nice big bonfire. When you did, you had something left that was called calcium oxide. What happened was we took calcium carbonate, we did a simple decomposition reaction, we made CO2, calcium oxide, and water. This was concrete. It was concrete because once you had the calcium oxide, you could take it, put it somewhere, mix it with water, let it react with atmospheric CO2, and by George, it made calcium carbonate again. So this light powder reacted with CO2 from the atmosphere to make a rock. This was rudimentary concrete. Now, think of limestone, calcium carbonate. How do you make calcium oxide? You heat the heck out of it, right? This is the tragedy that happened at Notre Dame Cathedral. It caught on fire. This entire structure is built of calcium carbonate. What happens when you heat it like this? It starts to degrade. That's why there's a really good chance that all of these walls, all these structures have been so weakened by the fire that they really can't be saved unless they're reinforced. Converted it to calcium oxide, and it's going to fall down someday now. That's a shame. The Romans, however, discovered a trick. In addition to limestone everywhere in the world, there's also sand. That's silicon dioxide. It's quartz. If you take your calcium carbonate and you heat it in the presence of sand, really interesting chemistry happens. This works best actually if you add salt water, not just water. You get what today is called Portland cement. In Roman times, they discovered this pretty much by accident, and they kept it a secret because this is the one thing that allowed the Roman Empire to build the most remarkable of structures. This isn't limestone clumped together. This is Roman cement. Now, you've driven down roads in Illinois, and you know that after a couple winters, they're falling apart. Roman cement was so good that this thing is still standing 2,000 years later. It's just an amazing cement. Nobody exactly knows the recipe. Again, if you were Roman and you made this stuff, you died with the recipe, or they killed you, one or the other. But it's remarkable concrete. All right, let's move up from the crust to the atmosphere. The Earth is surrounded by this atmosphere, so it's everywhere. It serves many, many purposes. It absorbs energy from the sun. It recycles water and other chemicals. It protects us from high energy radiation. The sun really just radiates all sorts of bad nuclear particles towards us, and the atmosphere helps protect us from that. And of course, the oxygen in this atmosphere is what we use to support life. Air, we call it air. It's a mixture. It's a homogeneous mixture. Nitrogen makes up about 80% of it. Oxygen about 20%. There's a little bit of argon, a little bit of carbon dioxide, And there's trace things, water vapor, ozone, methane, whatever, that make up this tiny sliver. We classify the atmosphere as having 4 distinct layers. The troposphere down here next to the crust where we live. The stratosphere is above it. This is where planes fly, stuff like that. You've heard of ozone. We'll talk about ozone. Ozone lives here between the stratosphere and the mesosphere. And up here, where satellites and shuttles and things like that, this is called the thermosphere. Now, the troposphere, this guy down here, is the lowest layer. It is 16 kilometers high, more or less at the poles. This is most of the mass, however, because of gravity, it pushes it down. As you go from ground level up the mountain, you decrease the temperature about 6 degrees per kilometer. Up here at the top, it's about minus 50 centigrade. I don't know what that is in Fahrenheit, but it's darn cold. Next, it's less dense because it has very little water vapor. And this is where the ozone lives. As you go up through the stratosphere, the temperature actually increases. Mesosphere. This is up where this is low Earth orbit, if you will. About 70 kilometers above the ground. Gases are very low density. Again, the temperature now decreases with altitude. And finally, we hit the king of it all, the thermosphere. This is very high Earth orbit. Gases readily absorb radiation because it's the very top. This is where the sun is blasting everything. And up here, the temperature increases with altitude. At the very top, it's estimated to be 1,500 degrees. Now, you know, in reality, that's a little misleading because the gas density is so low up here that you would very occasionally get hit by a molecule of gas. But if you did, it would be really energetic, really hot. So it's really hot, but there's not much of it. This translates into the cold vacuum of space. Now, we've all heard of the greenhouse effect. The greenhouse effect, here's our atmosphere. We have sunlight coming in whenever the sun shines, not today. Okay, that's good. The light from the sun comes down, it warms the earth. When it does, the earth, because it's warm, emits infrared radiation. It does this in all directions. If we have something that we call a greenhouse gas, and this is water vapor, CO2, ozone, methane, and a bunch of others, these organic molecules absorb the infrared radiation. When they do, they begin emitting at a slightly different wavelength their own infrared radiation. Now, about a third of this stuff that they're emitting is reflected back towards Earth. So greenhouse gases absorb the infrared radiation, change the frequency just slightly, but radiate it back towards Earth. That causes the Earth to warm. It's a very small effect unless you happen to have way too much CO2, methane, ozone, or whatever. All right, speaking of CO2, yeah, in the last 100 years, our emissions of CO2 have grown at least 15%. Why did this happen? Because we went from growing plants to an industrial lifestyle. We also discovered fossil fuels and we burned the heck out of them. We also discovered automobiles and we drove the heck out of them. They make CO2, it goes up, it's a greenhouse gas. Global warming, even though it's a very slight effect, it's still enough. It's such a delicate system. Can cause the ice caps to melt, that causes flooding, the oceans warm, the animals in the ocean don't quite know what to do now, so they die. We have huge storms that are forming now. It's basically a bad thing. We'll talk a little bit more about that in a minute, but let's talk about another greenhouse gas that's actually beneficial, and this is ozone. Now, ozone, as we said, lives in the stratosphere. It absorbs high energy ultraviolet radiation. If there was no ozone and you walked outside, you would be fried. Ozone absorbs this and basically protects us. That's good. However, in the stratosphere, there are compounds, man-made compounds, that have been found to release radicals. These radicals react with the ozone and make oxygen instead, which is good, but it does not block ultraviolet radiation. These things are called chlorofluorocarbons. They were commonly used in air conditioners, spray cans, and for cleaning machine parts. They were just as common as they could be when I was younger. Fortunately now, we don't do those. If we zapped our ozone layer by this chemistry, replaced it with oxygen, again, the UV light would just radiate down on us. It would be a very bad thing. Lots and lots of skin cancers, and you basically could not go outside. Kind of like now. Isn't that bad? You've heard of UVA and B. Well, it turns out that ozone blocks UVB. This is the shorter wavelength. It is higher energy, and it's the stuff that can really burn the heck out of you. UVA is good. That's no problem. Doesn't give you deadly sunburns. Well, the age of satellites came about in the late 60s and the early 70s, and scientists were clamoring to put every detector that they could on a satellite. When they did that, they suddenly noticed that, oh my goodness, this is Antarctica. There's a region over Antarctica that every year the ozone layer gets really thin. Now, of course, that means you can't sunbathe in Antarctica, but okay. But they followed up on this. The reason that this happened, again, was because the chlorofluorocarbons make chlorine radicals, converting ozone to oxygen. Chemistry of this is something like this. Radical is a molecule with an unpaired electron, extremely reactive. It could react with another molecule, regain its hydrogen, but leaving only one electron. This again is another radical. An example of how this is happening in the upper atmosphere. This is Freon 12. If you take a really strong light, like sunlight, and you shine it on this fluorochlorocarbon, you will break off a chlorine radical. Now, what happens if there happens to be ozone present? The chlorine radical will react with ozone to give a chloroxide radical and oxygen. That in turn forms a peroxide. This is a weak bond, however. It can break, form a peroxy radical and chlorine radical. Now, if you're paying attention, we started here with a chlorine radical and we wound up with one. That means that once we make this entire process happen, we've converted ozone to oxygen and we're back to where we started. So we can do this over and over and over a billion times. And when we do that, it eats the ozone. Well, this was one of the original pictures. And yeah, there's a hole here over Antarctica. This, of course, was followed up. This is 95, 96, 97, 98, going all the way up here to 2002-ish. For some reason, in 2002, things really weren't so bad. They got better. Probably the reason was that back here in the 70s, so way back here, everybody realized the chemistry that was happening. And chlorofluorocarbons were outlawed. You could not use Freon 12, etc. You had to find something else. And more or less, over the next 20 years, things did seem to get better. However, not everybody plays by the rules. 2012, it got worse. 15, even worse. 18, not so much better. It is very slowly healing, but there are countries, developing countries around the world, that are still using Freon. They shouldn't. It's done illegitimately, but it's still happening. And it's a bad thing. This year, for the very first time, an ozone hole of significant magnitude was also observed over the Arctic. Now, this is an animation, a set of stills here, that results from a calculation. If we had not outlawed Freon 12 back in the early 70s, this is what the calculations say the ozone would happen all around the world. This is North America, which is our world. So let's go 74, 94, 2009. By today, we would have very low ozone. By 20 and 60, it would basically be gone. Fortunately, we did outlaw these things. Most countries in the world are following the rules. We need to make sure everybody does. Like I said, the Arctic is also doing the same thing. Now, this is a time-lapse photo here. This is the polar vortex. We're all familiar with that because it slipped down over Chicago, and that was bad. You'll see that within this vortex, there's a region where we have a significant ozone depletion. By the end of March, it looked like this. This is the very first recorded ozone depletion over the Arctic. So once again, we really do have to take care of this. Any questions? All right, we're all very familiar with our friendly coronavirus, and it's very bad, right? But it has had one very interesting effect. Automobiles burn fossil fuels, and when they do, they emit things. Carbon dioxide, like we said, for greenhouse gases, but they also emit nitrogen oxides. Now, every time you take your car in and have it tested, which is a real bother, one of the tests that they do is for the level of nitrogen oxides. That's because nitrogen oxide, if you take NO2 and you add water to it, what would you get? One hydrogen, one nitrogen, three oxygens. That's nitric acid. Nitric acid, it gives ugly brown stains on your hands. It's a strong acid. It's a really nasty compound. This is what happens from vehicle emission. Well, when the coronavirus was still getting started, January 1st, 2020, this is a satellite image of China. And the color here reflects concentrations of nitrogen dioxide. You can see here, this right up here is going to be Beijing. It's a very industrialized area, lots and lots of NO2. So this was January. Everybody stayed at home. 1 month later, look at this. My gosh, you could even see Beijing. The nitrogen dioxide pollution had dropped tremendously. Let's just look at it again because it's so amazing. Here we are, January. By February, it was basically gone. People were so amazed when these images came back that they went and they looked at it historically. This is January, February, and late February of 2019. Same region over China. Really bad NO2. If you look at the images from this year, almost none, none, and even less than none. Just an amazing effect from the fact that people were not allowed to go out, drive cars, run factories, and stuff like that. So there's a benefit. This also tells you just how resilient our atmosphere can be. We can go from something like this to something like that if we just stop doing the bad stuff. Instead of gas cars, electric cars, whatever. All right, let's talk a little bit more about the greenhouse effect. We said greenhouse gases absorbed infrared radiation, and then they radiate it back towards the Earth. That's where the greenhouse part comes in. That's what happens in a real greenhouse. From 71 to 2005, vehicle emissions, including NO2, rose from 1.8 billion tons to 4.6 billion tons per year. It's a lot of CO2. Global air temp went up, at least half a degree centigrade, that's 1 degree Fahrenheit in the last century. By the time we hit 2000 or 2100, we expect at least a 2 degree centigrade warming. This has given us almost a foot rise in sea level in the last 100 years. This is a plot, CO2 versus time. Again, it's gone up quite steadily. If you go back and look at the records, starting in like 1880 and going all the way to almost today, this is global temperature. It zaps around a bit. And this is CO2 levels. The correlation is phenomenal. Now, people say that, well, gee whiz, the Earth undergoes natural cycles. And they're right, it does. If you go back to, well, a very long time ago, and you look at the global temperature as best we can measure it, using the fossil record and whatever, as a function of time. So this is 2,000 years in our window. Turned out that it was a little bit flattish for a while. We hit in the medieval times, so around 1,000, a warm period where it was warm. That was followed by a remarkable time when it dropped. Now it only dropped here a little over half a degree. But this set off what was widely called the Little Ice Age. The Little Ice Age struck mostly in Northern Europe and even in England. This is an etching from the time. This area here, this is a river. This is the Thames River in the middle of London. London Bridge is somewhere. This froze so solidly that they actually used it for fairgrounds. Everybody just went out and had a good time on this ice. Again, this was a temperature decrease of actually less than 1 degree centigrade. It is suggested that if we continue the global temperature increase, in addition to the things that we've talked about, such as giant storms, that we're going to melt the ice caps. This is Arctic, and as you can see, this poor polar bear is having a hard place to find a home. If the Antarctic is now melting at a phenomenal rate, we'll see that in a second, that could cause massive flooding all along the coastal areas. This is Antarctica. Now it's cold in Antarctica, isn't it? It's worse than Chicago. This is an island on the tip of Antarctica, and it's a satellite image. It was getting warm, like in the 60s, believe it or not. I want you to note the ice sheet here over this stretch of ocean and on this little island. In 1 week, this is the change that was observed. The ice sheet is disappearing, and we now see dry land and little lakes.
Mr. Young, do you think now that we've been on isolation, like maybe that has like a lot less of the Antarctica ice has melted?
Yeah, I mean, sure. The less we do, the less we mess things up, the better off it's going to be. But, we have to live. Here's again the same thing. This is the ice sheet. Note here, no lakes, nothing. There it goes. lake, no ice sheet. And that happened in 1 week. There were people, literally people, swimming in this region of Antarctica. Now, they were very cold. It's worse than Lake Michigan, but nonetheless, they did it. It's just astounding. If we do nothing, it is projected that by the time we hit the end of the century, that we will have a global increase of up to 7 degrees. That's going to consume all of our coastal cities. Here in Chicago, if we're 7 degrees, that's roughly 15 degrees Fahrenheit as an average temperature increase. It's going to be really hot. All right, well, most people in the world can sit back and look at this and say, gee, this is a bad thing. And to everybody's credit, the world got together to talk about it. Issues. Should we limit growth? Do developing nations have a right to increase their emissions? The problem of global warming is so vague that can people really grasp it? And frankly, it has become so incredibly political, fear of the unknown, nobody quite knows what to do. Nonetheless, in 2016, the world got together in Paris and they signed a document. Every country in the world to hold the global average increase to well below 2 degrees and try to get it down to 1.5. Every country in the world. This was a great thing. Sadly, in 2017, Trump announced that the United States was going to withdraw from this treaty because he thought it was stupid. Earliest we could withdraw is November of this year, and he has notified them that we are withdrawing. That's not a great decision, I don't think. That's my society part of the course. Mars once had an atmosphere. It had oceans. It was a great place to visit. It's climate changed, and now it's this ugly brownish red desert. You have to wonder if we're in for the same sort of thing. And really, you need to think about this. Do we have any questions? I'm sure we do. We all do. Nobody knows the answers. Once again, on Wednesday, we're going to do chapter 16, and we're going to understand why fat doesn't make you fat. Following this lecture, quiz 2 and sample E2 will come online. We have a week or so to do quiz 2. Same thing with sample 2. This is the modified syllabus. So we're here. We just did chapter 12. Quiz 2, chapter 16 on Wednesday. E2 review a week from right now. A week from Wednesday, exam 2 comes online. You will have 2 attempts at this online exam. Each attempt has a 1-hour time limit. It will cover basically everything since the first exam, a little bit from chapters 11, 12, and 16. If we have to take a final exam, we will have a review the following week, and then the final exam on the 13th. Speaking as an educator, I hate final exams. Final exams are cruel and unusual. In general, everyone's grade drops one letter on taking the final. It's just a horrible thing. I don't think it's a great educational exercise. Therefore, let's try really hard to hit our point level here on exam number 2 so we don't have to do this. Here's our list of tutorials. Again, this is your way out of the final. Please make sure we do them. Do we have any questions?
Professor Young,
Yes.
hit the 306 point level. We only miss out on the final, not the second exam, correct?
That's right. You typically it's around 310. Again, I haven't calculated it because I haven't actually figured in these sample exam points, but it's around 310. And if you hit that level, you get an A. You don't have to take the final. Great offer. Don't mess it up. Any questions?
Nope, I'm pretty good here.
All right, I'm good if you guys are. Have a good night. Please take care, and I will see you Wednesday for Chapter 16, Human Nutrition.
Perfect. Thank you, Mr. Young. Have a wonderful night.
Thank you, you too.
Professor Young,
Yes.